All right, welcome everybody. In today's lecture, Bipin Butala, the Director of Software Development here at Aston Technologies, will be going over some of the tools that we use on a daily basis and some of the situations or scenarios that we provide technical solutions to our clients. So one of those things that comes up quite a bit is creating a REST API or finding a way to get to data, say if it's in a database or a message queue or some sort of file system or something like that, and send it across the web so it can be consumed by a web app, some sort of mobile app, really anything that uses the web. So at Aston Technologies, we have two main pillars of expertise. One of those is the app dev or web app dev pillar or business unit, which I lead, and we do a majority of our work in the back end using a tool called SpringBoot, and it's a way to rapidly build APIs using Java and the Spring framework, which makes using Java much more modern and easier. And the other big pillar that we have here at Aston Technologies is our network engineering and network consulting, where we manage everything from designing enterprise network infrastructure to maintaining it, to tuning it, to looking for security holes or hardening access with firewalls and so on and so forth. So I am going to give a little overview of how to create a simple API using SpringBoot, just to give you a little bit of a overview of what that's going to look like. This is the sort of Tomcat SpringBoot API or application represented in a diagram. It's going to connect to a MySQL database that just has some fake bank data, and I'm going to expose that over the web so that it can be consumed by a web browser. But along the lines, I'm going to, Dan's going to come up here and talk about how by doing that, there are certain implications that anyone can hop in on that stream, and some of the things or measures we can take to secure or prevent a Unabomber-esque person from seeing our secret data. So with that, I'm going to go ahead and get started. Like I said, I use a tool called IntelliJ, and I'm going to give you a quick overview of that with a new project. I don't think I can change the size of this font, so apologies. But basically, I am just creating a new project using Java, Maven, and then I'm going to bring in some dependencies. One of the powers of Spring and SpringBoot specifically is that it's really, really easy to set up things from the initial dependencies to actually get something running. It uses what they coined as sensible defaults. So instead of installing an application and creating a bunch of configuration and setup to get going, to get bootstrapped and up and running, it provides default configuration for almost every scenario. And if you need to modify that or do something different, you can override that configuration. So it kind of goes with what it calls sensible defaults, which means like if you're out of the box, it'll just get up and start running. And if you need to modify that to your needs, you can always override that. I'm also going to use a tool called Spring Data. Again, it's all part of this Spring ecosystem. And it makes interacting with a relational database really, really simple. So along those lines, get this up and running, and then so this is IntelliJ. On the left, we've got our project sort of structure. I know it's small in the back or to the audience here, but there's very few files that you really need to get going off the bat. So I'm just going to delete a few things that come by default in here that we're just not going to use. So right out the gate, it comes with we're going to use two files, actually three. There's a POM XML, which just has all the dependencies. If you're familiar with Node, it would be like your package.json file. And so that allows us to bring in, all this other great code and use it in our app. Along those lines, we have the entry point, which is just a Java file that's annotated with the SpringBoot application. You'll notice these annotations. I'll use these quite a lot. They are prefixed with an @ symbol, and they are preprocessors. So before the code is compiled, certain rules are enacted, and they can be quite powerful. So really, this is all you need to start up a simple web app. It's not going to do anything, but it'll be there. And then you have your application properties, in which you can override some of those defaults. So for example, the Tomcat server in SpringBoot runs by default on port 8080, but most of the web traffic is on port 80, at least for HTTP. Its defaults to port 80. So I'm just going to go ahead and start at port 80. I'm going to show you how in IntelliJ I can connect to a data source. So on my laptop here, I've got an instance of MySQL running with a simple table that represents some bank data. So all I'll do in here is just MySQL, punch in my username and super secret password. And then I've just created a database inside of this called bank. And then we'll test this connection. Now, there's not really any reason that you need to necessarily use this part of IntelliJ to connect to the data. I'm just showing it to you so that you can visualize the database that kind of sits, behind the scenes or under the hood on this laptop here. So as you can see, it made a connection. There is a schema called bank, and there's a single table in there called account that's got just some dummy data for us to play with, right? So nothing too complex there. But again, I just wanted to show you that data so you can kind of visualize what's going on. So what we're really going to try to do is find a way to enter an account number and then get back the balance and whatever account owner details we have. And in the last Tech Talk, I built an iPhone app using Swift UI that was almost identical to what you see running right here. And I just modified it so that it will actually reach out across an API. And if we punch in an account number, it should retrieve that. But we haven't built it yet, so obviously nothing there. So I am going to get into it now. What we need to do first off to connect our, I'll show you again what we're doing here. We're going to build this JPA to MySQL connection right here. And to do that, we first need to create a Java class that represents this account table. They're often called entities. And I'm just going to name this thing account. Account. And a magical annotation we're going to throw at the top here is entity. This is using something called JPA or Java Persistence API, and it automates or simplifies connecting a Java application to a relational database. So I'm going to do that. I'm also going to use a tool called Lambert just to prevent me from having to create getters and setters. Now, as you can see, it's starting to bark at me a little bit here. It says a persistent entity should have a primary key. So then we can put any number of fields and data types we want inside this entity, but we need at least one that's going to refer to the primary key of that table. And if we look back here in account, maybe you can't see it, but I've created and we can see the DDL here. So this is just the SQL to create the table. And I've marked the account number as the primary key for this table. So that's what's going to be used to look things up. It's also going to be indexed by default. So close some of these things. Okay, so I need to, and that was a string, and I called it I called it account number. And that is going to be annotated with @ID. So what I'm doing here is I'm telling Spring Data and JPA that this field right here is the one that I want you to treat as the identifier. I just need to bring in the import. Okay, and really all we need to do after that is just match the fields. We have account owner, balance, password, username. Account owner, password, username are strings. Balance is going to be a double or a decimal. So just go ahead and do that. So I have string, account, owner. I've got string, I think I call it username, string, password, and then a double of the balance. So this will represent all of the fields, and this is sort of a Java container that we can put the data that we get from our database into, and it'll serialize it into JSON going up eventually, and also we can use it to write to the database as well, which we're not going to cover in this one, but just be aware that's there. So I have this container. Now really all I have to do outside of that is create an interface. So this is the real power of Spring Data. Spring Data will give you all basic relational database CRUD operations by default by simply extending an already existing interface. I'm going to call this thing account repository. And all I need to do here is extend CRUD repository, which is a Spring Data interface that has pre-built, here I'm just going to jump into there, pre-built methods for all the common kind of database interactions that you're going to do. So this is like all the base ones, and if you need to create more custom ones, you can easily do that within the interface. And to do this, we need to tell the CRUD repository just two things. We need to tell it that the type, so that's going to be the account entity that we just created, and we need to tell it the data type of the ID. So that was not an integer. That was or was it an integer? It should be an integer, but I think I called it a string here. There we go. All right. So with those two things in place, I now have all basic create, retrieve, update, and delete functionality available in my database, or in my Spring application. So I'm going to go ahead and fire this up. There's a couple ways you can do it using IntelliJ. This is the main entry point, so I could have just launched it from here. Otherwise, it's probably too small for you to see, but there's a little play button up top. So it's saying, hey, we can't, I don't know, the URL data source isn't there. That's because we need to not only tell the application what the table looks like, we also need to give it the connection string to get us into that. So I'm just going to punch in Spring data source, and we're using the MySQL driver. And the URL is going to be JDBC SQL localhost 3306. Bank is the name of the thing that we create, the schema. Data source username. I think it's root. Spring data source password. So with that in our application properties, which is identical to what I used to connect to the database here in the IDE, the application should have enough information to go ahead and start. So I'm going to fire it off again. Hopefully things bounce up. So okay, so the application started. It's not doing anything yet. Let's create a little test just to make sure that we can see that data that is available. So if we want to use that repository that I just created, we use a concept called dependency injection to auto-wire that in. Account repository. Now, this is another, this is really the core of what Spring is. It's a dependency injection engine. And the Spring context, its primary function is to figure out which dependencies to use in which context. So with that, I am going to create a test and void db connection, we'll just call it. I just want to have a little sanity check that things are actually, I can actually get to the data that's in the SQL database from the code here. Did you see that? Okay, too. So account repository has a bunch of helpful methods, as I showed you before. And one of those is find all. And this will just retrieve everything in the database. It's a little bit the nuclear option for what we're doing here. If you say had 10 billion records in your database, it would not be a great thing to run. But since we only have 4, I am going to just go ahead and stick with that. So if we run this test, hopefully what I should see printed out to the console below here is all of the data serialized. There it was for a second. There it popped up. As you can see, I'm getting that data now into my test, which means that the connection between my database here and my repository layer in my application is good to go. So with that in place, I'm now going to set up the API or the REST API endpoints. So I'm going to make URL paths that will then return return some of that data. So to do that, I'm going to create another file here, Java class. I'm going to call this account rest. So you see there's account rest controller. And to tag this as a REST controller, you intuitively name it or annotate the class as REST controller, which means that Spring is going to inject this controller as a mapping between URLs and Java code. So we are going to need our repository in there. So I'm just going to wire it in just like we did in the test itself. And then I am going to create an endpoint. So an endpoint or a URL or a resource is going to get is going to be the suffix to the server. So at www.google.com is going to be my server /Gmail. That would be my endpoint, right? So I'm just going to create a little dummy one here. It's just going to be called we'll just call it hello, and then let's see, public. It's going to return just a string. And we'll say greeting. What you name the method doesn't really matter. I'm not going to pass anything in right now. And I'm simply going to return hello, Aston Tech Talk audience. Okay, with that in place, I am going to restart. Oops, that's just going to run the test. Okay, so with this up and running, and what you don't see here, but I'm going to move to a little more detailed view of this. Again, just to review, we use JDBC and Spring data going across port 3306 to connect to our SQL database server there. And then inside of Spring, by default, there's a web server, if we bring in the web package, which I did, and that's Tomcat. Tomcat is a very popular server. It's actually built into a lot of Cisco products that are out there, as well as tons of other things. And it's a really streamlined web server that will run Java. So you don't really need to interact with it specifically, but it can run as a standalone application. But in the case of SpringBoot, it lives inside of the application itself, which makes it very convenient and easy to spin up. I don't have to install some server and then put my code on that server. It's all baked right into the code. So that's what I wanted to talk about. Tomcat is our web server, and it's not really, it's kind of, again, under the hood or behind the scenes doing things. So our app is up and running. The URL is hello. For the sake of this demonstration, am running everything on localhost. But of course, in a real world, that we push to an actual server, maybe in AWS or somewhere out there in the wild. So I am still on HTTP because that's what comes by default. Localhost, I called it hello, I believe. Hello. Okay, so we've just created our first endpoint. We've got our web server up. It's not doing much, but just to kind of review, we are going to now take care of this kind of connection between the data layer and the API layer. So I'm going to want to create an endpoint that will take an account number and then just give me that information back. So I need a way to get data into my endpoint. So let's just modify our example a little bit here and pass in what's called a path variable or a path parameter, which means, I don't know what I call this, account number. That's right. So this is going to allow me to take data in the URL and pass it into this method here. So I'm going to annotate path variable, and it's going to be an integer, and it's going to be called, we'll call it account number just for consistency. No, I don't want to do that actually right now. I'm just doing string name. And then instead of this, we're just going to concatenate some strings together to prove that we're taking information from our URL, it's getting into our method, put smash together between hello and exclamation marks, and then return back. So restart real quick, make sure that's up and running while that's going. So hello now is expecting a parameter at the end. And if I say Dan, hit enter, it'll take that information displayed. So again, not very wowing or whatever, but just kind of showing you how we get data from the URL or the request body or maybe query parameters into our controller method. So, all right, let's do something that's got some actual meat to it. So I'm going to use get mapping, I'm going to create another endpoint. And this endpoint is going to be /account/ and then I'm going to put in curly brackets here, account number. It's going to be very similar to the last method we created. Oops, that's not what I want to do. We're going to name this thing public, or it's a public method, and we're going to use a response entity, which is a kind of wrapper for the response. It allows us to add custom headers, change the response code from 200 to 201 to whatever, 400, 500 for errors and stuff like that. So we're going to use a response entity, and inside of it is going to be, in the body of that response is going to be an account, hopefully, if we find it from the account number. So we'll just say get account details, and this is going to have a path variable, and that's going to be an integer. Oop. And it will be called account number. Again, it doesn't really matter what I name it here, but for consistency, I'm going to stick with that. So now we're going to return not a string, but we're going to return a response entity with a builder OK. OK is a 200 response. And in the body of this response, I am going to use the account repository, find by ID, and then pass the ID that's coming from the path parameter into my repository method. This returns an optional, and just for the sake of this demonstration, I'm just going to retrieve it. An optional is another wrapper in case it doesn't find it. You won't get a null pointer, but that's for another discussion. So with this in place, I've created an endpoint, account / whatever number we put in place, and it's going to pass that number down to the repository that we created, which is then going to go into the database, query for that, get the data back, serialize it into JSON, and send it back up, right? So again, just to look, I'll restart it while this is flashing. Again, you know, the point here is to be able to get to that bank account data from a browser across, we're still on 80 here, across normal HTTP unencrypted traffic, and should see the data. So in that, I put the endpoint as account, and then 1541 was one of the accounts. Oops, it likes to default to HTTPS. So sweet, so there is our data. So we have created an API that goes all the way through that, you know, that you can, an API running on Tomcat that's connected to a relational database, MySQL. And if we pass an account number, it'll retrieve that record in the database. In my Xcode project here too, for that iPhone app, I'm just hitting localhost account and then passing in a number that I'm getting from this input field here. So now 1541, if I run account balance, it actually connects out and gets that data. So with that kind of all built and in place, I'm going to hand it over to Dan, who's going to show you why what I did right here is totally susceptible to some sort of packet capture or nefarious man in the middle.
Hello, everybody. My name is Daniel Lambert, or Dan Lambert is generally what I go by. I'm a network engineer for Aston Technologies, and my goal here is to called Wireshark, which is able to actually look inside of a data stream between, you know, two computers that are communicating and show us the literal ones and zeros that are transmitted to and from the client and the server in this case. So we already have Wireshark pulled up right here, and actually I wanted to start that off by showing that this is a free and open source tool that we can just go to www.wireshark.com. It's not .com though, I'm a liar. Wireshark.org. And so from this site right here, you can just simply go to the download option, and whatever operating system you're using, it'll go ahead and give you a nice little indicator of what you should download on your machine in order to run Wireshark. Now, Wireshark itself is simply just a tool to actually view packet captures. And what a packet capture is a literal it's an organization of the actual ones and zeros that are sent from one network interface to talk to another one. When you actually install this, it's going to want to install a bunch of other stuff on your computer. In a Windows computer, it's called WinPCAP. I actually don't know what it's called inside of an Apple computer, but those extra drivers are the actual software that listens on the network interface cards inside of your computer and actually tracks those ones and zeros and is capable of saving them as a PCAP file. They're usually just .pcap if you ever are viewing them in the real world. And then Wireshark is the tool that can open that .pcap file in order for you to actually see the ones and zeros. So Wireshark is kind of like Notepad. PCAP files are kind of like .text files. So when we get Wireshark open like this, we have a list of every single interface that's on our computer. We don't just take a packet capture from a computer, but we rather take packet captures from network interfaces themselves. And in this case, we'll probably be focusing mostly on the loopback in order to see the traffic that Bipin created today, because he's hosting the web server inside of this computer, and we're using this computer to access that web server. So none of this data actually ends up out on the actual network. But before I do that, I'll go ahead and take a packet capture of just some general Wi-Fi traffic and show you guys what it will look like, in the wild on the computer. So I'm going to remove any filters that are currently on there. I select the Wi-Fi interface, and just by hitting the little blue shark fin hump at the top, I actually begin the packet capture where we can start to see packets come through. It's broken up into 3 separate windows. The top window here is an ordered list of all of our different packets that are coming in from the network. They're ordered from the first packet since I started the packet capture that was red, and it just incrementally counts up one by one. It tells us the time since we last heard our last packet, or since the beginning of the packet capture, and gives us kind of a plethora of other information. We're not going to try to teach everything about Wireshark today, because since we're actually literally looking at the ones and zeros, you'd have to literally understand every single protocol that's running on a network in order to really get it, and honestly, I don't know all that stuff. So we're just going to focus on the things here that we do want to touch on. The middle window is actually going to break out and understand or interpret the data that was pertaining to each individual packet. So I can select different packets, and you'll see the bottom 2 windows are changing between different data types. If we focus on the bottom here, we can see the actual literal ones and zeros as they transmit across our network. Something that I think is kind of an important takeaway, or at least it was a big aha moment for me when I was learning networking, is that all data on networks are transmitted linearly. The ones and zeros have to, there's a first 1 and 0 that gets sent, and then each 1 and 0 afterwards linearly came after that. There wasn't like 2 sent in parallel. And then every chunk of these data, say 1,500 bytes worth of ones and zeros, becomes what we would call a packet. And those packets are sent linearly, just as we're looking at the top. So the ones and zeros are, everything can just be strung along into like one big long chain. So those ones and zeros, though, are pretty hard for a human to interpret. Technically, if you were good enough, you could look at these ones and zeros and start to be like, okay, I see everything that's inside of this packet because I just know how these protocols work so well. But I would say the vast majority of human beings out there can't do that. And so Wireshark is a tool that allows us to actually get some human-readable data from this. And that's what this middle window is all about. There ends up being a few different dropdowns that we have here, and each of these dropdowns is a different portion of the packet. In fact, if I click this part right here where it says Ethernet, and you'll see that got highlighted in red, down in the bottom portion, it's highlighted the ones and zeros that make up that part of the packet that was sent. If I then click a different section inside of here, you'll see it'll highlight those. And you may even pick up as I click down these one by one, it's jumping around, so it makes it a little hard to see. But it starts with the Ethernet header. Those are the very first ones and zeros. Then it goes to the next header, the next layer we sometimes call it, inside the packet, which happens and starts immediately after the previous layer, and so on and so forth until we get to the entire contents of the packet that's sent. So obviously by default, packets don't have human readable data, and that really is Wireshark's trick. In order to have that middle pane show us everything, it uses a tool called dissectors in order to do that. We can actually take a look at all of them by going to Wireshark, Preferences, and we can take a look at protocols right here. There's a giant list of protocols that exist inside of here, and they all have various, parameters you might be able to modify about them. But any, protocol that's been had a dissector, we would call it, created for Wireshark. When you then run Wireshark to read these ones and zeros, it will match any ones and zeros it sees to the relevant dissector and then display that data in a way that we can actually interpret it. So maybe just to walk through one of these packets, we have the very first packet here. And we open up the very first part of this, just the frame section. And we'll see it highlights all of the bits there. The first section here isn't actually any of the ones and zeros, but it rather talks mostly about time. It'll tell you the first layer of encapsulation that's used on the packet, so it knows how to start reading the very first ones and zeros. And then it tells us stuff like the timing of when the packet was actually sent. Epoch time, really commonly used in networking or really any kind of computing. It's counting up from, I believe, January 1st, 1970. And so if you're looking at maybe multiple different packet captures and you're trying to compare times, epoch time can be a reliable point to compare against. We would call this, in networking, the layer 1 portion of the packet. Layer 1 refers to the physical layer, and if you ever hear network engineers say, oh, we're having a layer 1 problem, it means something is physically wrong with stuff. It's not that anything was configured. It's like someone literally went and unplugged the cable or clipped the cable or intentionally damaged the device by pouring water on it. So that's the first layer of what we would call the OSI model. Now, as you get deeper into a network, each of these different dissectors or layers inside of here, we go deeper into that OSI model, which has a total of 7 layers, although we kind of ignore 2 of them. But the very next layer is layer 2, and in this case it's called Ethernet, and it's the very first set of ones and zeros. Now, by default, Wireshark knows to interpret these as ones and zeros, or as Ethernet, because these were captured off of an Ethernet interface. So, you have different types of layer 2 protocols out there, although the vast majority of what a network engineer or a data network engineer is going to focus on are all Ethernet networks. The actual protocol that makes up the first ones and zeros is pretty much universally dictated by the interface that you're plugging into on the device. Is this an Ethernet interface, or is it a fiber channel interface? And if we expand the contents of what's inside of the Ethernet interface, we'll see this isn't actually displaying all that much data. Ethernet's a pretty simple protocol, and the relevant information is actually quite short. We have a source and destination MAC address, which again, by clicking them inside of here, we can highlight the actual ones and zeros down there that make up that actual data. And these are hardware addresses. These are addresses that are physically on the network interface card of either the sending or receiving device that we're sending to. They can be a little bit thought of as like your name, right? So as a human being, we each have a name. MAC addresses are sort of like the network interface card's name, so that we can identify it when we're looking inside of here. And it's also used for, actually being able to know where to send packets. But you'll notice this next field right below it where it says type, and that's the field I really wanted to focus on. After, Wireshark's dissector has gone through all of the ones and zeros that make up Ethernet, it's exactly 64 bytes for Ethernet, it needs to know how to think about the next layer of the packet that it's reading. And the way that it knows that is there'll be a type field in the Ethernet header that has 2 bytes given, as we can see from the highlighted red part, of how to interpret the next zeros and ones that come inside of this packet. In this case, we can see it's using IPv4, or we could just call it IP for the most part. There are a couple other versions, but if we open that IP header, we've now moved to the next layer of a network engineer's OSI model. We've gone from layer 2 into layer 3. Layer 3 is always going to be encapsulated inside of some layer 2 protocol, in this case Ethernet. So the IP header here has a little bit more information. There's a little bit more that goes into IP, but the main thing I want to focus on here is that we have a source and destination IP address. The source address is quite literally the address that's on the computer that we're sourcing the traffic from. And then the destination address is quite literally the thing that we're trying to talk to's IP address. Now the difference between a MAC address and an IP address is pretty simple. That's more like your home address. It can change, and as the physical piece of hardware moves to different networks and moves around the world, you're not always going to have the same IP address, but typically you'll keep the same MAC address. And then just like the previous protocol of Ethernet, we have a field in here, this time called protocol, not to be confusing instead of type, but that tells, not just Wireshark, but the receiving computer how to interpret the ones and zeros that happen in the next section of the packet. So it counts through all of the layer 3 packets, and it's like, okay, the next layer is going to be interpreted as a TCP packet. Open up the contents of this, we can see all of the different things that make up the TCP packet. The key thing in TCP packet that we can probably correlate to Bipin's part is the source and destination ports that are chosen. Currently, his web server that he built is listening on TCP port 80. And so the source port, or the destination port, when we look at his traffic, we'll actually see is going to be using port 80. And then there'll be always a source port from the client that's sending it. Ports aren't one-sided. Now, in the TCP field, you don't actually have a type or a protocol field. So, our dissectors inside of Wireshark, or our receiving computer, doesn't necessarily know how to read that next layer, although clearly it does here because it's automatically figured out that it's using the TLS protocol. So the way that that happens for Wireshark is it's actually implied. It saw that the conversation was using a particular port number, in this case 443, and by and large that's the standard that we would use for TLS traffic on any network. And by just nature of that being 443, Wireshark is going to jump to conclusions and try to interpret that as a TLS packet. On rare occasions, it would happen where the ports and the dissector don't align and you get a bunch of gibberish as a result. But you can go into that protocol fields I was showing you before in preferences, and you can actually modify things to get it to be like, okay, this protocol is actually running on this port, or vice versa. So that's how Wireshark figures it out. Your computer figures it out literally by the configurations that would exist on something like Tomcat when he actually stood up the web server. When he configures that and says, listen on port 80, he's told that server, that computer, and that operating system to actually open up port 80 on that computer. And if you ever hear any traffic come into that, interpret it this very specific way. Since it's an HTTP web server, that is how that server would then know to interpret the next bits, zeros and ones in that packet, as the next layer inside of the Wireshark capture, or inside of the packet. So that's kind of an overview of generally, we've talked about kind of the OSI model and the different layers. I guess I skipped TCP is the layer 4 from IP is layer 3, and then technically TLS skips 5 and 6 and goes directly to 7. That happens a lot where we don't really use the OSI layers 5 or 6 at all. So let's stop this packet capture and start another one where we're actually going to try to see the data that Bipin created in his little program. So this time I'm going to choose to stiff the packets off of the Loopback interface rather than the actual Wi-Fi interface that was inside of this computer. And the purpose of that is that, again, the web server is inside of this computer. We're going to be testing using this computer. All of the packets are contained inside of this computer. And so if we just sniff the Wi-Fi interface, none of those packets actually are going to get transmitted out of the computer. So it's not really, useful here. But if we go ahead and start the packet capture on the Loopback interface, we can go ahead and create some data. So here I could just refresh this page and go to it there like that. And in theory, I have some new packets, which I do. We'll show again that we can also do it with the phone application here in just a second to kind of show that they work the same way. Now in the top field of Wireshark here, we have the ability to apply our own filters. I mean, of course I could just start scrolling through this and look for whatever data I actually want, and in this case there's not much there, so it'd be pretty easy. But normally network engineers are getting packet captures that are thousands, tens, or hundreds of thousands of packets long, and you're not just going to scroll around until you see the one you want. So this filter page at the top allows us to look for specific things inside of here. And in this case, I know he is using an HTTP application, so I'm going to type HTTP in the top and hit enter. It's actually pretty nice how easy a lot of these filters are inside of Wireshark. You think what it is, you type it in, and it happens to be a real filter. I feel like it's pretty well thought out. And then we can see two packets here that these do actually represent, I believe, the traffic that we just generated. So I can go ahead and select this whole thing, and I can hit follow this TCP stream. It'll pull up some data here. We'll actually be able to see immediately that we're already seeing that data in plain text as it would have happened across the network. This little window is just a summary that Wireshark creates for us. The red is the packets that our client sent. The blue is the packets that our client received. And it'll just show us the raw data as it sought. But we can also just look at it inside of here. And now we're following the specific TCP stream. Now getting into a little bit deeper into the network side, these first three packets that we'll see that are noted as a SYN packet, a SYN-ACK packet, and an ACK packet is a unique property of the TCP protocol. Without going into depth on it, TCP is a protocol used by networks such that if ever a packet is lost across the network and random things can happen, a computer didn't function quite properly or something is causing packets to not make it all the way to the endpoint successfully, TCP can detect that those packets were missed, and then it's capable of resending all the packets that were missed. In order to do that, though, it has to create a session, or a socket, we sometimes call it. And in order to do that, this three-way handshake must be completed. So anytime you're looking at any web traffic or any TCP traffic at all, you're always going to see it start off with a SYN, a SYN-ACK, and an ACK packet. In fact, if you ever look at TCP traffic inside of a Wireshark capture and it doesn't have that, then you didn't catch the very start of the conversation. You're seeing the TCP, you started the packet capture after the TCP conversation had already gone online. Now, you can see in the protocol field, it identifies each of these packets as TCP packets. And if we kind of shrink this middle section again and get rid of this bottom section, it's not as important now. We can see that we only go up to the TCP field here. There is no extra layer on top of this packet. The packet actually ends at this point because it's just part of TCP's three-way handshake. But after that completes, we do get to an HTTP packet, as I have highlighted here. And we get that additional layer that's added. Now here you're going to see that there was a GET request sent. This is part of the API that Bipin created. It's used heavily by the HTTP protocol to request files from different systems. And we can see the request URI of account/150 or 1541, which I believe, if you have that pulled up somewhere, your IDE.
It's just to the right all the way.
To the right all the way? Huh? We won't worry about that for right now. I'll let Bipin re-show that when he's on there, but this section right here where we see the account/15141, that is exactly what we put in the top field after localhost up there, and that was directly written into his programming language that's what or in his IDE, what the account was actually, or the program is actually listening for. So inside of Wireshark, we send that request, we see that URI, and then Wireshark sends a few more packets, and we finally get down to this 200 packet. This is the final receipt packet that is returning all of the data that we requested. Now, if you look at this section right here that I currently have highlighted, you can see it's two reassembled TCP segments. So ultimately, all this is trying to show is that oftentimes you're trying to send things that won't fit inside of a single packet on the network. Or maybe this content isn't too large, but if you're sending a 4K image or a video file of some sort, there's no way you're getting that entire thing inside of a single packet and slamming it through the network. And so it'll get broken up into lots of little packets. And then Wireshark figures that out for you. It's part of the dissector, and it will go ahead and figure out, hey, look, I have those two TCP packets above, specifically number 85 and 87, which you can see here's 85 and then 87 is the one we're actually on. It's like I've reassembled that data to represent, the actual data that was flowing between the server and client at that moment. And we can scroll down through all of this, close the HTTP layer, and then we can see the actual content of the payload of the packet. At this point, to a network engineer, we don't really care what's inside of the JSON stuff because we're usually only operating on the first 4 layers of a network. But, you know, we can see the unencrypted JavaScript or JSON formatted data in here. And you can see all of the different, you know, key value pairs that were inside of that. And we could see we can get the bank account balance, we could get the password. And let's say I had a really large packet capture and I was trying to target a specific person. I could go through the effort of taking this figure right here, going, I want to apply this filter as selected. And up here at the top, it's automatically just generated what the filter would look like for me to search for a JSON formatted string in that packet. And then I could just go ahead and change what's inside of the quotes right here to be any name I wanted. And then I could target a specific person if I was trying to look for their data. Moral of the story though, Wireshark, while it's super useful to a network engineer when they're troubleshooting things on the network, is also super useful to a malicious attacker, where if they're able to be anywhere inside of your network where they could plug in a computer and start to sniff the packets like we're seeing here, if you don't encrypt the data, they would be able to see it in plain text just like this. And I will hand it over to Bipin now to talk a little bit about securing that.
Thanks, Dan. All right, there. So I was just saying that a common scenario is one that we've just encountered here as far as, you know, I'm a developer building an API for our bank's new iPhone app or mobile app, and I build it, and then the networking team or security team says, this is completely not okay because you have it completely unencrypted, and anybody can see this information, and we'll get sued and go out of business. And just got our mobile app off the ground. So, so in order to do that, I don't really need to change anything about my API, but more, here, actually I'm gonna go back to our diagram. More so, I need to change the protocol that Tomcat is listening on, right? By default, Tomcat was listening to HTTP traffic, and by default it's on 8080. I overrode that to port 80, but I need to continue to configure Tomcat to operate using SSL or TLS on HTTPS on port 443. So first off, I am going to go into my application properties here, and I'm going to change from port 80 to port 443. It would be great if that was all you needed to do, but unfortunately that isn't all, because not only do I need to change ports, I also need to enable SSL. So, okay, another super easy thing to do. But beyond that, I need to create some sort of secret, some sort of very complex key, if you will, that can be shared and will allow the information to be encrypted and then on the other side decrypted. So the JDK, or the Java Development Kit, which is kind of the underlying code language that everything that I'm doing here in Spring and IntelliJ runs off of, has a tool that's built in called KeyTool. If you install the JDK, you get KeyTool with it. And just by running it, a command line tool, I can pass it a bunch of options. One of the things that KeyTool will do is it'll generate a key pair and a certificate for me. And this is what I'm creating now is called a self-signed certificate, right? It's not correlated to any certificate authority, so your browsers would still be confused by it, but the traffic on it will be encrypted. So it's a bit of a long command, but you know, this information is readily available on the internet, and also there'll be links to everything that I've done and some of the things that Dan has done too in the meeting notes afterwards. So I'm going to give this key pair an alias. I'm just going to call it Aston. I'm going to give it an algorithm, RSA. As far as I know, this is one of the most common algorithms for encryption. I'm going to give it a key size. Just go with 2048. I believe the larger the key size, the harder it is to crack. I'm going to pick a type. This is going to be a PKS file, a PKCS12. And then I'm just going to give this file a name. I'm going to call it Aston P12. And then just a lifespan, a validity of 365 times 10, so 10 years. So I'm going to hit that. It's going to prompt me for some information. I'm just going to create a dummy password. And now we want some metadata to bundle into the key pair. So I'm just going to give it, this is where I'm signing it, my dev, organization Aston, Minneapolis, Minnesota, okay, and then this looks good. It's going to crunch away, and now I should have a P12 file. It says it's a binary file. Do you want to see it? Sure. Yes. So it's just a bunch of garbage, right? Not very useful to us. But inside of that, we just need to now attach this P12 file to our Tomcat server. So it knows whenever it's listening on port 443, any requests that come in to encrypt them on their way out. So I've created this self-signed key pair, and I just need to move it. It showed up down here. I'm just going to create a folder inside of resources called key store, and I'm going to move my P12 file in there. Now, I don't know if you could see, but I was prompted to create a password and an alias for that key store, this P12 file, if you will. And I just need to tell Tomcat, first, a few things. I need to tell it the key store, which lives in our class path. I put it in key store / Aston P12. I need to tell it the store type, which was PKCS12. I need to tell it the alias, which I just called Aston, and the password, the key store password. Oops. Which I just called password. So similar to our database connection, I'm just passing in some information that relates to that new key that I gave, or that I created. This key pair P12 file that I created. So with these pieces in place, I switched ports to 443. I enabled it. You got to turn it on, and then gave it this information about the P12 file that I just created. And so now, hopefully, when I restart, we're moving from port 80 to port 443, which is the default for HTTPS traffic. And it didn't have any problems starting up. As you can see, it's running HTTPS on port 443. So let's hop over to here. Now, instead of HTTP, I'm going to do HTTPS, localhost, accounts, account. So now, now Firefox is barking at me, say, hey, this is not secure. This potential security risk, right? I'll go look at it. Localhost uses an invalid security certificate. If I wanted to get around this, I'd have to register my certificate with a certificate authority. Can't remember what some of the names of those are, but it's basically a service that is held in high authority that you pay to register your certificate with. And you'll see in places like Wireshark, I hope Wireshark has it, but that the connection is secure and that the certificate matches the name. But since I'm running on localhost, it's a self-signed certificate, I'm not going to get that here. But I'm going to go ahead and accept the risk and continue because I know what it is. But what you will see is if I go here, connection is not secure, but if I look at more information, I'll see that the technical details, probably very hard to see. I don't know how to change the font here, but that the connection is encrypted, and it talks about the TLS protocol for that. So, here I am doing my new development, and the network team got on my case about my unencrypted API. So here it is. I've created my encrypted API. So hopefully this should stand the test of Dan's packet capture here. And again, I'm running on 443, so we'll see what happens from there.
All right. So let's see if we can see that traffic now. Just to add a little bit to what Bipin was just describing about the certificates, which is all super true about getting the certificate actually registered with the certificate authority. The ultimate thing that's happening there is, well, the certificate is a multi-purpose tool. It's actually used as a public key and part of the encryption of the packets that we're encrypting here. It's also used as an identifier. So it's a little bit like a driver's license, to use another human metaphor. And if you don't get your driver's license registered like from the DMV, then people probably aren't going to trust it. Basically what Bipin did when he self-signed a certificate on the computer is he went to his home printer and printed out an ID. And if he tries to go buy alcohol with that, it's probably going to get turned down because they don't trust that authority to actually authenticate that. So getting it registered with one of the profound authorities like VeriSign, or even Google does some, or it looked like Cloudflare was the one that did, Wireshark. These have gone through a significant auditing process with all the different operating systems and browsers to be trusted sources by default. And so if you pay them, get your certificate trusted, they're obviously going to validate that you're actually allowed to have it the same way the DMV would validate you are who you say you are before giving you an ID. Then any computer that goes to it could reach it without that certificate error. So coming back here to Wireshark, and one thing I actually just want to confirm before we get too far in here. All right, perfect. So I'm going to stop this packet capture. We're still on the loopback, so I'm just going to restart another packet capture directly in here. I'm going to replace the HTTP filter back on here. And we're just going to go ahead and hit go on that. Continue without saving. All right. I'm just going to go and try to generate some traffic right here. That is still HTTPS as we saw before. And if I come back to Wireshark, doesn't see anything this time. So what's happened is Wireshark has that dissector that's looking for HTTP traffic, and technically it's looking for port 80, but even then it would not be able to see any portion of the HTTP header at this point. So let's clear the filter and actually try to look for it. Well, what's some information we know about it? We know that its destination port for the server he has built is using TCP port 443. So what I'm going to do is I'm going to expand the TCP part here, select the destination port, and I'm going to hit the apply the filter as selected there. And now I have a new filter that I can change the number on. I'll be like, I want this to be 443. And I hit enter. And so now I'm looking at traffic that specifically is coming from our computer to the web server on port 443. We can see the source and destination. Those IP addresses are localhost IPs. That's the IP your computer will forward traffic to when it's forwarding it to itself, and that's why we see the source and the destination is the same here. The source port is kind of randomly selected by your operating system. It's called the ephemeral port, and then 443. So from looking at this, I'm actually going to just right-click one of these and go to follow this TCP stream like we did before. And you'll see we kind of get a bunch of gibberish this time. So this time I'm not actually just plainly seeing the data immediately when I get this filter up. And if I actually look inside of this, well, I still see the TCP three-way handshake. You know, this is kind of an important thing to note. Your Ethernet layer, your IP layer, and your TCP layer, those don't get encrypted. If you were to encrypt that data, it'd have no idea how to get it there, right? You might be sending a really important piece of data through the mail that you don't really want anyone to get the hands on, but if you just scribble all over where you're supposed to write the address, it's not going to get there. So same concept here. We have to leave that stuff unencrypted. But that final layer, the layer 7 where HTTP happens, well, we're not going to be able to see that. We see a TLS handshake happen here. That is the security protocol that was used to encrypt the data here. Part of HTTPS would use TLS or SSL encryption. And eventually we see it complete, and then we just get these chunks that, you know, say application data. And that's where the actual data is that we are sending. But we can even use Wireshark and drill all the way down into that TLS layer, like so. Oh boy, I'm having clicking problems. There we go. Then we have the encrypted data. So that's about the bulk that we could see now. Now we trust in cryptography in general and that these different encryptions are still working suitably and that they haven't had some massive exploit such that a hacker could figure out a way to reverse engineer this. But the modern protocols we're on are and currently, to public knowledge, not easily exploitable. And when it becomes public knowledge that one doesn't work, we typically move to other versions. That's actually how we ended up on TLS 1.3 or 1.2 that we use now. You know, there were many predecessors before this, but as exploits became public, they would rework it and rebuild them such that there weren't any. And so if we were actually a man in the middle here, plugging into some router on the internet or somewhere in the middle between where this traffic was traveling, we would not be able to see the actual contents of the API that Bipin had created. Now, there's one kind of catch here, and Wireshark is a useful tool. Obviously, something can decrypt the data because the server sends data, the client receives the data, and then it's able to actually see it in plain text. And there are something called private keys. There's a private key that's stored on your server that should never leave the server and no one should ever get it. Same thing on the client side. When it goes to visit something, it'll have its own private key that it'll generate and use in order to create this session. Now, those are supposed to be exclusively local inside of your computer, and you shouldn't be able to you know, some hacker listening in the middle of the network shouldn't be able to gain access to that. But this is a good point to bring up the importance of not clicking phishing emails, because if you clicked a link that you weren't supposed to click in an email, like someone was trying to target you to gain access or be able to unencrypt your data, simply clicking that link could effectively forward your private keys to them. And then if they got this data in the middle, they'd be able to use that private key to unencrypt the data. So how might that work? If we stop this packet capture, cancel. We're going to find that terminal window again. And that one right there. Perfect. I'm going to run a script that Bipin created beforehand. We're not really going to go into the details of this, that restarts the entire script for us and has also created this special file inside of the computer, which we'll be able to point Wireshark at, which is our local private keys effectively, to unencrypt the data. If we go to Preferences, we go to Protocols, we scroll through 2 million of them, we get to TLS. We can point this pre-master secret file. All right, how am I going to? Users.
And then Aston developer.
Aston developer. There it is, the SSL key file right here. We're going to hit open, and now we've told Wireshark for its TLS dissector to look for private keys inside of that file. And so if we hit OK, we're going to go ahead and start another packet capture right now. Continue without saving again. This time I am just going to filter on HTTP. We scroll back over to this. We try to regenerate that data HTTPS. If everything worked, we can now see the data plain text inside of there again. So that data was still encrypted on the wire, but if someone gained access to that secret key file, or that, the secret key file, and was able to plug it into Wireshark this way, just as before, they'd be able to go to this packet, scroll down, and see all of the actual raw data that existed on that network again. So be very careful clicking links that you don't really trust. And I think that wraps up.
Yeah, thanks, Dan.
Yeah, no problem.
So yeah, at this point, we'll open up to questions that you have about anything that we covered today, taking it beyond that, on the networking side, on the dev side, anything. Oh, sorry, I totally can't see.
No,
I couldn't see.
Yeah.
No.
So back at this when I was doing that.
Absolutely. Yeah, they're very similar. Sometimes they'll just be called network administrators. Sometimes they'll be called network engineers or senior network engineers. Been around a little bit longer. Same thing with the senior network admin. There's also network architects, which are people who would be more on the design side and less on the administration side. Engineers sometimes bleed into both categories. Honestly, it kind of just is up to the company that's making the job rec what title they want to put on it. So.
And did you have a question back there?
Yeah, I was going to ask the RSA algorithm that it uses to encrypt it. Is that similar to like SHA-256?
Is it? They're very similar, although both end up getting used, because SHA is a hashing algorithm, whereas RSA is like the actual, it's the name of the whole suite that does the encryption. So you have encryption algorithms inside of there too, like AES or triple DES is the name of one. There's a few different encryption algorithms, there's a few different hashing algorithms, and then all of that gets encompassed in RSA.
Good question. Yeah, Joe.
Are there any special considerations when building an application for use outside of the U.S. cryptographic region?
Oof. Yeah, maybe not so for the actual application itself, but any piece of hardware that is able to run encryption algorithms in general, be that SSH or the HTTPS that we're looking at here, that is dictated at a government level, what is actually allowed and what the standards are that has to be deployed to. So, and
Yeah.
You were using Spring as like a dependency injection engine.
Mm-hmm.
Is there like a JavaScript or C# equivalent for that?
I'm not sure for C#. I know there is. I don't know what it's called in the .NET world. But for JavaScript with Node, specifically in Angular, I know that you can use. It's got dependency injection built in, constructor-based dependency injection. I'm not sure if React has something like that. But to answer your question, I believe there are packages you can add on that will do it. But it's not as mature or commonly used to use dependency injection as far as a design pattern in a JavaScript application. But good question. So the question was, is dependency injection used, what is the equivalent of Spring's dependency injection engine used in JavaScript? So, yeah. Guys got any more questions? Anybody? All right, sweet. Well, if there's nothing else, I'd just really like to thank everyone again for attending and look forward to seeing everyone in these future events. So thanks again.